our conservation of momentum situation, but in order to have conservation of momentum, what do you got to have? Collisions, right? Things have to bounce off of each other first. And sometimes they bounce off each other and sometimes they don't. Sometimes they stick together, right? So let's look at collisions where the two objects bounce off of each other. They don't stay together. They bounce off each other. We call this an elastic collision. And you can think of it as elastic. Collision. An elastic collision. Okay. So here we've got one object and it's hitting another object like so. And I didn't do that justice. Let's do this over again. Let's have it be two balls. Two balls that collide and they both are deformed. Okay, so normally they have a radius r and that radius gets deformed on the side of the collision. So that's a better collision right there. And then they bounce back. So here's initially going in like this. We got ball 2 and ball 1, ball 1, ball 2. And then after, of course, ball 1 is going this way, and so this is before, during, and after. So what happened? What did we see that happened? The same thing that happened in our other. If the two masses are equal, the same thing that happened with the last collision that we saw, they changed, excuse me, they changed their velocities. So the velocity of number 1, look at that, very nice. What a mess. The velocity of number 1. That velocity, V1 initial, ended up being the same as V2 final when the mass is 1 equals to the mass 2, and we could just say that they both equal m. Those two ended up being equal. Well, it's the same here. This guy goes that direction and so does that one. So that means that V02 equals V final of 1. Okay. V initial of 1. Okay. So at any rate, that's an elastic collision. But let's really do some, let's define something here. The internal kinetic energy is the sum of all the energies for all of those things. So the internal kinetic energy is the sum. And why did I put Nobody knows. Nobody knows why I do what I do. Internal. Again, lovely. Internal kinetic energy. That would be the sum of all the internal kinetic energies. So that's the kinetic energy of mass 1 plus the kinetic energy of mass 2. IKE. Well, that's 1/2. And if they have the same mass, then it's 1/2 m times v1 squared plus v2 squared. And it could be v1 initial, v2 initial in the initial situation, but that also has to equal v1 final squared plus v2 final squared. So that's our internal kinetic energy, the total internal kinetic energy. We could also call that KE total, which is kind of how I like to see it. For our billiard balls that we saw in the last video, we had V10 is equal to 0.4 meters per second. We had V20 is equal to 0.1 meters per second. And we want to make sure that KE initial equals KE final. KE total initial equals KE total final. Nice. Let's do it. We've got 1/2s all over the place. So we've got 1/2 m, and we're going to do V1 initial squared plus V2 initial squared, and that's going to equal 1/2 m V1 final squared plus V2 final squared. But the 1/2s can go away, and we're left with these guys, okay? And we can square it. We can go 0.14 squared, 0.4 squared plus 0.1 squared. And we already figured out what these are, right? So it's obvious. 0.1 squared plus 0.4 squared. Now you might say, well, I know they're all going forward, but in this situation over here, we've got V1 final going backward. And that's true. But when you square a negative, you get a positive. So you may as well just keep it all positive and work with it in a positive way. And there's nothing like being positive. This is 0.16 plus 0.01. And we're going to all add all that stuff up, meters squared per second squared. And it's going to be the same over here. 0.01 plus 0.16 meters squared per second squared. And that just equals 0.17 meters squared per second squared. Now, if we want to multiply by the mass and divide by 2, we can do that. That'll give us our energy, but these two things are equal, and that's the important point. Okay, so we've got that. Great. What about inelastic collisions? So let's look at inelastic collisions. For an inelastic collision, the internal kinetic energy is not conserved. Okay, not conserved. So IKE initial does not equal IKE final for inelastic collisions. Okay, so how does this happen? So let's talk about the physics of it. What happens for this? Well, what do you think? What do you think? First, you have to have the right pen size. Then you can write something that doesn't look crazy. Two ways. One, the objects could stick together. Like when you throw Play-Doh and it gloms on to something, your book or something, and it just gloms right onto it. Those two items are now stuck together, and you threw it at your book and it's stuck. That's fine. That can happen. You've got that. Then we've got the objects are deformed, and that deformation takes energy out of the system. Now, it doesn't always take energy out of the system like we saw before. They could deform and then snap back. That's fine. But if the objects get deformed, but, and that's a but, the objects get deformed but don't snap back. So that would be like your car getting hit and then the bumper pops right back out, right? Okay, well, they're designed not to pop right back out, so you don't get hurt. However, imagine that they did, so the objects get deformed, the bumper goes in, and then it snaps right back out, and the energy that went in is the same energy that came out, so that gives you the elastic collision we just saw, right? These two guys are not deformed after, and they're not deformed before, right? They're only deformed during. So the objects get deformed, but they don't snap back. Okay. That deformation takes energy, and it takes it out of the system reducing the IKE final. Relative, right? That the IKE final is relatively smaller than IKE initial. So it just has to be smaller. So they're not equal. It turns out that IKE, because of the way entropy works and time and all that, the final has to always be less than the initial. Because final is after the collision happens, right? So after the collision happens, you've got less kinetic energy in the system. So far, so good. Let's do an example or two of these elastic and inelastic collisions. So imagine we've got a goalie and we've got a puck, a hockey puck. There's the hockey puck. Okay, our goalie is going to look like a big wad of cotton. Okay, and they're blocking the goal. It's huge. It's big wad of cotton. Okay, and this is before. And this guy right here is coming in with the V puck. And of course, that's the mass of the puck. And then finally, we have this kind of situation like that, where the goalie has glommed on. So we've got mass of goalie, we've got mass of puck, we've got velocity of puck, we've got velocity of goalie, which equals to 0 at first. After, we have a total mass, and of course that's the mass of the puck plus the mass of the goalie. So that's our total mass, and because of conservation of momentum, there has to be a velocity, because over here our momentum initial for the system, m goalie times v goalie is 0, right? And 0 times 0 is 0 times anything is 0. And so then we're left with the initial is the mass of the puck times the velocity of the puck. So great. After, in order for us to maintain conservation of momentum, we do the same thing. But now we have our total mass, because they're all together, and that is going to be our V final. So let's draw out a few things that we know. The mass of the puck, 0.15 kilograms. Mass of the goalie, 70 kilograms. Nice small light goalie. And velocity of the puck going in. Somebody gave it a slap shot, and it's doing 35 meters per second. What a big mess we have down here. Okay. So we've got that. Let's figure out what our question is. Our question is, what is the recoil velocity, or V final, of the goalie and puck combined? So, what is V final? Well, we've kind of already done all the work because we just have to say that these two guys are equal to each other. So our mass of the puck times the velocity of the puck equals our mass total times our V final. And we can then do a little algebra and see that our V final is equal to our mass of the puck divided by our, I'm gonna take this and stick it in here. Mass of the puck plus mass of the goalie, and that's times the velocity of the puck. So I rewrote that equation here, and I'm gonna take this out because that looks ugly. And there we go. V final equals mass of puck divided by mass of puck plus mass of goalie. So what is that? Let's plug in some numbers. Yeah, so 0.15 kilograms. We're going to multiply that by our velocity of the puck, 35.0 meters per second. And we're going to divide that by the total mass of puck plus goalie, and that's 70.15 kilograms. And you notice kilograms cancel and we're left with meters per second, which is exactly what we want for a V final, right? So V final is equal to our 7.5 times 10 to the minus 2 meters per second. Okay, awesome. B, what is the loss in kinetic energy? So how much energy did we lose for this whole thing? How much energy was transferred? And we'll talk about where it was transferred from and to in a second. But the loss would have to be, so loss of kinetic energy. What would you say the loss would have to be? Keep in mind, IKE initial has to be greater than IKE final. If it's greater than, the difference between the two is the loss. So we can say IKE 0 minus IKE final equals our loss. So what do we have initially? Our KE initial is equal to 1/2 m puck v puck squared. And we're going to subtract off, we're going to minus off our KE final, which is 1/2 big M times V final squared. So we can do the same old thing where you take equation 1 and you subtract equation 2, or in our case we'll be adding them together, but that addition is a subtraction. So we've got 1/2 MPVP squared minus 1/2 big M V final squared. And that equals something. So 91 It ends up being 91.9 joules. Okay, you do the math. I'm not doing it. We need to keep moving forward. 0.196 joules. So this is our IKE final, this is our IKE initial. And what we are finding is the loss. So this minus this is going to be our loss. Well, this is roughly, this one here is roughly 0.2, right? So if we subtract off 0.2 from 91.9, we've got 91.7. So our delta KE minus delta KE is equal to 91.7 joules. We lost 91.7 joules in the collision. Okay, awesome. Let's do a little bit of something here. Where did that energy go? Let's talk about it. That energy went into pain for the goalie. That energy was absorbed. By the goalie. So, it's not always fun to be the goalie because they took a little bit of a hit on that one. That's okay. Let's do collisions in 2 dimensions. Change our color. Collisions in 2D. Okay, collisions in 2D. First of all, you have to keep in mind that all of the balls, we're going to just deal with balls, they're considered point particles, okay? So if we really want to think about it, we think of this ball, that point, so that's number 1, hitting another point, number 2. But it's really the whole ball, right? The whole ball is hitting the other whole ball. But we are thinking about point collisions when we do this. Excuse me. Okay, so let's do a couple. In fact, I don't like what I've drawn here. Let's get going back to this. Let's have this ball hit this ball, and they're in line with each other somewhat to a point. When they hit each other, one ball is going to go flying off in this direction. We're going to call that theta 1, and that is the velocity of 1. And this is 1, and this is 2. And then this guy is going to go off at theta 2. And that's velocity 2. Okay, so if we define our coordinate system like this, so there's our x and there's our y, we can say in the x direction, P total equals the only ball that's moving. So V2 initial equals 0. V1 initial equals V1 initial. We'll talk about what that is in a little bit. We can plug in a number. But our P total initially is totally in the x direction, and it's M1 V1 0. Okay? All right. So, where do we go from here? Let's define a few things. Let's break down our V1 final, and our V2 final into their x and y components. So we'll do y component. And in that color, and what's another good color? I don't know. The x component, so that's V1 final x, and this one is V1 final, V2 final x. So we've got our x components, we've got our y components, and now we can start doing our sum. Okay, should we talk about, or maybe it's clear to you guys, I hope it is, that the sum I need to pause. No, I'm not. I'm not going to pause for a second. Thank you. Sorry about that. Okay. Momentum. Let me get back to where we were at. Our momentum in the y direction. Okay. Well, that initial momentum in the y direction has to be equal to our final. But what was our initial momentum in the y direction? You guessed it. It's 0. So, in the y direction, we only have V1 final y, and we're going to add to it V2 final y. But V2 final y in our system is negative. So we're going to come over here, and we're going to select negative. So that's negative. And that has to be equal to 0. So our V1 final, M1 times M2, or M1 times V1 final y, minus M2 V2 final y, have to be equal to each other. We haven't said anything about those two things being, the two masses being equal. So we have to keep them separate. They could be different masses. Okay, good. That's our conservation of momentum in the y direction. Now let's do the x direction. Well, let's write it all out actually. M1 V1 final y is V1 final times the sine of theta 1, and M2 times V2 final times the sine of theta 2. Those have to be equal. So that is a statement that we can count on. We can call that equation 1 if we want to. I don't know if I want to or not, but I'm going to. And let's do x now. We have x, this is before. Now we're going to do after. So after, we've got initially, let's just do after m1 v1 fx plus m2 v2 fx, and of course we know that that equals m1 v1 final cosine of theta 1 plus m2 v2 final cosine of theta 2. Those things have to be equally to each other. So I'm going to bring this guy over and put it right here. m1 v1 0. And that is our second equation. So we've got some sweet equations going on here. And if we go into the book and we look at 8.7, we can use their numbers. M1 equals 0.25 kilograms. M2 equals 0.4 kilograms. Our V1 initial is equal to 2.0 meters per second. Our V2 0 V2 0, that's equal to 0. We already said that. And we also know that theta 1 is equal to 60 degrees. And we are given also V1 final is equal to 1.5 meters per second. So the question is, we've got two, but basically the two questions add up to one thing. The question is, what is V2 final? And when I put a little line over the top, it's a vector. So when we say what is V2 final with a little line over the top, that means we need to know the magnitude of V2 final. So we want to know V2 final magnitude and theta 2. So once we know both those things, we'll know the magnitude and direction, which is essentially what we need for this. Okay. All right, so how do we do it? Well, we have a couple of equations. We've got a lot of unknowns. I'm going to use what we know and what we don't know. First, in the y direction. In the y direction, I'm going to underline with this bright color what we know. What do we know? We know theta 1. Okay, what else do we know? We know mass 1. We know mass 2. So we know mass 1 and we know mass 2. We know V1 final. Very nice. And we don't know theta 2 or V2 final. So we can solve for V2 final sine of theta 2. So I'll circle that in this color. If we solve for this, that would be great. Now let's go back to our other equation. And equation 2, we know this. We know V1 final. We know theta 1. We know M2. We don't know this. We know this and we know this. Now look, if we have both of these things solved for each other, we can take both of those things and do V2 final sine of theta 2 over V2 final cosine of theta 2, and we'd end up with V2 finals canceling each other, and it would give us the tangent. So we just need to figure out what those two items are and get the tangent. So I'm going to leave it to you guys because my page is not, I don't have a lot of page here. And let's do halfway, and then we'll move to the next page. So V2 final sine of theta 2 is going to equal M1 V1 final sine of theta 1 divided by M2. Okay, that was equation number 1. That one's easy. Okay, so we've got one equation. The other equation, well, we have to subtract this so from both sides. So we're going to end up with V2 final cosine of theta 2 equals M1 V10 minus M1 V1 final cosine of theta 1, and we're going to divide it all by M2. So we have two equations, and we can take one of them and put it in the denominator. This would be our denominator. And this would be our numerator. So when we do that, we're going to get a sweet, sweet equation. V2 final times the sine of theta 2 over V2 final times the cosine of theta 2 equals the tangent of theta 2, because these guys cancel, and that equals M1 V1 final sine of theta 1 over M2 divided by M1 V10 not equal to minus M1 V1 final cosine of theta 1 all over M2 and I don't know if you guys know this or not, but this would be like dividing a half by a half. And that ends up giving you 1, so you can get rid of the M2s. And let's see if we can get rid of that guy right there. So, all in all, we end up with tangent theta 2 is equal to 0.325 over 0.3125. Theta 2 then is the arctangent of that. And that is 46 degrees. Okay, but we still have not found our V2. We haven't found V2 yet. Our V2 final, we need it. So we gotta keep moving. We can look, we can go back, we can say, okay, where does V2 final? If we know this, let's do the easier of the two equations. Let's do the y equation. Let's do this one. I'll circle it in this bright color. We're going to do this equation. We can plug in all of these numbers. We can plug in this number, or we could just send the sine of theta 2 down to the other side over there, and we'll have our V2 final. If we do that, then I'm going to go back to our page below, and we end up with V2 final is equal to our M1 V1 final sine of theta 1 divided by M2, and here I've moved the sine of theta 2 down to the denominator from the other side. And that equals our 0.32 over 0.29. Kilograms all cancel out, and we're left with meters per second. So that's fabulous. Our V2 final is equal to 1.13. Now we can stick this on there and say it's 1.13 meters per second. And that's fine. But our answer needs to look like this. V2 final equals 1.13 at 46 degrees from the x-axis, positive x-axis. And then we box that in. Okay guys, thank you so much for your time. I'm going to upload this right now, and you guys can have at it.